Hi everybody, so in this video we continue with Chapter 9, Vectors, Lines, and Planes, specifically Section 9.4, Lines in Space. In the same way that a plane can be defined by any 3 points, a straight line in space can be determined by any 2 points A and M that lie on it. So here we have A and point M as well. Alternatively, the line can be determined by specifying a point on it and a direction given by a non-zero vector parallel to it. To investigate equations that describe lines in space, let's begin with a straight line L that passes through point A, which has coordinates x sub 0, y sub 0, and z sub 0, and parallel to the vector v, which is equal to ai plus bj plus ck. This should be a c here, as shown in figure 9.26. So if L is the line that passes through A and is parallel to the non-zero vector v, then L consists in all the points M for which the vector AM is parallel to v. This means that for the point M to be on L, the vector AM must be a scalar multiple of v. That is, vector AM is equal to t times v, where t is a scalar. This equation can be written in coordinate form as x minus x sub 0. So this would be vector AM. Now remember that the coordinates of A are x sub 0, y sub 0, and z sub 0. So this is vector AM, and this is equal to t times the vector v. Remember that A, B, C are the components of vector v. Therefore, this equals TA, TB, TC as a vector. Now, for two vectors to be equal, their components must be the same. So that means that x minus x sub 0 should equal t times A, y minus y sub 0 should equal t times B, and z minus z sub 0 should equal tc. So if we rearrange this, we're going to get that x is equal to x sub 0 plus at, y is equal to y sub 0 plus bt, and z is equal to z sub 0 plus ct. And these are what are called the parametric equations of a line. So now let's take a look at example 9.20. And part A says, find parametric equations of the line through A, 1, negative 2, 3, and parallel to V, which is 5i plus 4j minus 6k. So that would simply be x is equal to 1, which is our x sub 0, plus 5t, where 5 is the x component of vector v. Similarly, for y, we would get that y is equal to minus 2 plus 4t, and then z is equal to 3 minus 6t. For part B, they want us to find parametric equations of the line through the points A, which is the same point A from the previous part, and B, which is 2, 4, negative 2. So here, first of all, we need to find a vector that is parallel to the line that goes through those 2 points, and a good vector would be AB. So vector AB, remember, is equal to 2 minus 1 is going to be 1, and then 4 minus 2 is going to be 6, and then we have that negative 2 minus 3 is going to be negative 5. So that would be vector AB. So that means that one set of parametric equations could be, if we take A, point A as a reference, it would be x is equal to 1 plus t, y is equal to negative 2 plus 6t, and z is equal to 3 minus 5t. An alternative solution would be using point B as the starting point or as the reference. So it would be x is equal to 2 plus t y would be equal to 4 plus 6t, and z would equal negative 2 minus 5t. So now let's take a look at a vector equation of a line. So an alternative route to interpreting the equation vector am is equal to t times v is to express it in terms of the position vectors r sub 0 of the fixed point A, which we can see here, and r, the position vector of m, which we can see here. In section 9.1, we discussed the difference of two vectors, which we can use here. Vector am is equal to OM, vector OM, minus vector OA. In other words, T times V is equal to R minus R sub 0. And this we can rearrange as R is equal to R sub 0 plus T times V, which is the vector form of the equation of a line. We can interpret vector equations in several ways. One of those ways has to do with displacement. That is, to reach point M from point O, or the origin, we first arrive at A, and then we go towards M along the line, a multiple of V, TV. So if we look at figure 9.29, for each value of t, we describe a point on the line. So for example, if t equals 3, this would be 3 times v, 6 times v over here, till we get to point M. Now, when t is greater than 0, the points are in the same direction as vector v, and then when t is less than 0, the points are in the opposite direction. We continue with example 9.21, and it says, find a vector equation of a line that contains the point negative 1, 3, 0, and is parallel to v equals 3i minus 2j plus k. So remember that the vector equation of the line is in the form r equals r sub 0 plus t times v. So for this case, it would be r is equal to minus I plus 3j plus t times 3i minus 2j plus k. Now notice that we can rewrite this as r is equal to minus 1 plus 3ti plus 3 minus 2tj plus kt. So notice that if we have that t is equal to 0, then the equation is going to give us the point negative 1 comma 3. If we have that t is equal to 1, then we're going to get that r is equal to 2i plus j plus k. If we have that t is equal to 3, we would get that r is equal to 8i minus 3j plus 3k, and so forth. So next we have example 9.22, and it says find a vector equation of the line passing through A, 2, 7, and B, 6, 2. So here we need a vector. AB would be a good vector here, and AB is obviously equal to 6 minus 2 and 2 minus 7. So this vector is going to be 4 and negative 5. So we can say that R is equal to 2, 7 plus t times the vector 4, negative 5. Another way of writing this, of course, would be that r is equal to 2i plus 7j plus t times 4i minus 5j. So let's continue with example 9.23, and it says find parametric equations for the line through A, negative 1, 1, 3, and parallel to the vector V, which is equal to 2i plus 3j minus k. So the parametric equations are simply going to be for x minus 1 plus 2t. For y, we're going to get 1 plus 3t, and for z, we are going to get 3 minus t. Now notice in this figure to the right, if we select a few points with their parametric values, we can see how the equation represents the line. For t equals 0, as we can expect, we are at point A. For t equals 1, the point is B. For t equals 2, the point is C. Now the arrows show the direction of increasing values of t. So we continue with line segments. Sometimes we would like to express a line segment in parameters. That is, to write the equation so that it describes the points making up the segment. For example, we want to parameterize the line segment between A, 371, and B, 142. First, we find the direction vector AB, which is going to be obviously minus 2, minus 3, 1, and then we use point A as a fixed point on the line. Thus, the parametric equations are these. Now, notice that when t equals 0, the line starts at point A, and when t equals 1, the line starts at point B. Therefore, in order to parameterize the segment, we restrict the values of t for t between 0 and 1, not including 0 and 1. So the new equation is the same, but we establish this limitation. In general, to parameterize a line segment AB so that we represent the points included between the endpoints only, we can use the vector equation r of t is equal to 1 minus t times vector OA plus t times vector OB, with t between 0 and 1, not including 0 and 1. So we continue with example 9.24, and it says parameterize the line segment through A, 2, negative 1, 5, and B, 4, 3, 2. Use the equation to find the midpoint of the segment. So we said that in order to parameterize a line segment, we would say r of t is equal to 1 minus t times vector OA plus t times vector OB. And we restrict the values of t for 0 and 1, not including 0 and 1. So that means that in this case, r of t is going to be 1 minus t times the coordinates of A, really, right? Because it's a vector that comes from the origin. So this would be 2 minus 1, 5 plus t times 4, 3, 2. And then from here, we are going to get 2 plus 2t for x. We're going to get minus 1 plus 4t for y, and 5 minus 3t for z. Now, in order to find the midpoint, t would equal 1/2, right? Because these values are between 0 and 1. So the midpoint has to be where t is equal to 1/2. So from here, we're going to get that the midpoint is going to be 3, 1, 7/2. Now this is obviously the result of plugging in 1/2 for t in these parameters. So now let's take a look at symmetric or Cartesian equations of lines. Another set of equations for a line is obtained by eliminating the parameter t from the parametric equation. So if A is not equal to 0, nor B, nor C, then the set of parametric equations can be rearranged to yield the set of Cartesian or symmetric equations. So notice that we have that x minus x sub 0 is equal to t times A, therefore t is equal to x minus x sub 0 over A. And then in a similar fashion, We also have the t is equal to y minus y sub 0 over b, and we have the t is equal to z minus z sub 0 over c. Now, obviously, because these three equations are equal to t, they also equal each other. Now, notice that the coordinates x sub 0, y sub 0, and z sub 0 are of the fixed point A on L, and they appear in the numerators of the fractions, and the components a, b, and c of a direction vector appear in the denominators of these fractions. So now let's do example 9.25, and it says find the Cartesian equations of the line through A, 3, negative 7, 4, and B, 1, negative 4, negative 1. So for this, first of all, we need a direction vector V, which we can say is a vector AB, and we know that this vector is going to equal 1 minus 3 for x, minus 4 minus 7, so minus 4 plus 7 for y, and then minus 1 minus 4 for z, and this is going to give us minus 2, 3, and minus 5. So this would be the direction vector. So when A is the fixed point, so A is the fixed point, then the Cartesian equations would be x minus 3 over minus 2 would equal y minus 7, so y plus 7 over 3, and this would equal z minus 4 over negative 5. Now, if b is the fixed point, then we would get x minus 1 over negative 2 is equal to y plus 4 over 3, and this is equal to z plus 1 over negative 5. So now let's focus on example 9.26, and it says, let L be the line with Cartesian equations. X minus 2 over 3 is equal to y plus 1 over negative 2, and this is equal to z minus 4. Now notice that this would be obviously the same as z minus 4 over 1. And it says, find a set of parametric equations for L. Now let's recall that the numbers in the denominators are the components of a vector parallel to L. So we can write it as u is equal to 3i minus 2j plus k. And then we know from the numerator that the point 2, minus 1, and 4 lies on L. So this lies on L. Now, that means that the parametric equations would be x is equal to 2 plus 3t, y is equal to minus 1 minus 2t, and z is equal to 4 plus t. Now, if they asked for the vector equation, what would it be? So a vector equation would be in the form r is equal to the starting point, right? So 2, negative 1, 4 plus t times the parallel vector, which is 3, negative 2, and 1. So now let's take a look at intersecting parallel and skew straight lines. In the plane, lines can coincide, intersect, or be parallel. In space, they can also be skew straight lines. Although these lines are not parallel, they do not intersect either. They lie in different planes. So these are skew lines in the three-dimensional space. How do we know whether or not two lines are parallel? If the direction vectors are parallel, then the lines are. We can check to see if the vectors is a scalar multiple of the other. Alternatively, we can find the angle between them, and if it's 0 degrees or 180 degrees, then the lines are either parallel or coincident. The case for coincidence is always there. And we need to check it by examining a point on one of the lines to see whether it is also on the other line. So here we have in figure 9.31 two intersecting straight lines, in figure 9.32 two parallel lines, and in figure 9.33 two skew straight lines. So these lines never intersect. So now let's take a look at example 9.27, and it says, show that these two lines are parallel. So line 1 has the parametric equations x equals 2 minus 3t, y equals t, and z is equal to negative 1 plus 2t. For line 2, we have that x equals 1 plus 6s, y is equal to 2 minus 2s, and z is equal to 2 minus 4s. So first, let's find the vectors that are parallel to these lines. So L1, let's say that L1 is a vector parallel to line 1. So this vector would be minus 3i plus j plus 2k. And then a vector parallel to line 2 would be L2. And this one is going to be 6i minus 2j minus 4k. Now it is obvious that these two vectors are parallel because notice that L2 is equal to minus 2 times L1. So now what we have to do is find out if they are coincident or if they are parallel. So notice that the point 2, 0, negative 1 lies on line 1. So this lies on line 1, right? I got that from here, right? This is the point. 0 for y and negative 1 for z. Now, what we need to do is find out if this point also lies on line 2. So let's pick y equals 0. So if y equals 0, notice that this implies that for the second line, 0 is equal to 2 minus 2s, which implies that s is equal to 1. So let's plug that into x. So x we know is equal to 1 plus 6s. So if you plug in 1 here, we're going to get that x is equal to 7. Therefore, that means that this same point does not lie on line 2. But since the direction vectors are parallel, that means that the lines must be parallel. So let's continue with example 9.28. And it says lines L1 and L2 have the equations, and they give us the equations, show that the lines are skew. Okay, so first of all, notice that the direction vector for line 1 would be 4, negative 4, and 5, whereas the direction vector for line 2 is going to be 8, negative 3, and 1. Now, these are obviously not scalar multiples of each other. Consequently, the lines are not parallel. Now, what we need to find out is if they intersect. Now, if they intersect, then there must be a point M. Let's call the point x sub 0, y sub 0, z sub 0, that is in both lines and that satisfies the equations for both t and s. In other words, x sub 0 should equal 1 plus 4t, which should equal 2 plus 8s. And then we would have that y sub 0 should equal 5 minus 4t, which should equal 4 minus 3s. And then z sub 0 should equal minus 1 plus 5t, which should equal 5 plus s. So what we have is a system of equations with 3 equations and 2 unknowns. So what we're going to do is solve for t and s for the first 2 equations. So notice that we can say, solve here first. And if we solve the system of equations, we're going to get that s is equal to 0 and t is equal to 1/4. So if these lines intersect, then these two values should make this last equation true. But notice that if we do -1 plus 5/4, this does not equal 5 plus 0. That means that the system is inconsistent. Therefore, the lines don't intersect and they are skew. So now let's take a look at application of lines to motion. The vector form of the equation of a line in space is more revealing than what we think of the line as the path of an object placed in an appropriate coordinate system, starting at position A, x sub 0, y sub 0, z sub 0, and moving in the direction of v, like we can see here in figure 9.35. So here we have the starting position at A and the vector v, which gives us the direction starting at A. Generally speaking, we can find an object at the initial location A represented by r sub 0. The object moves on its path with a velocity vector v equal to abc. The object's position at any point in time after the start can then be described by r is equal to r sub 0 plus t times v. Assuming the unit of time to be seconds, the equation tells us that for every second, the object moves a units in the x direction, b units in the y direction, and c units in the z direction. So for example, after 2 seconds, we find the object at r is equal to r sub 0 plus 2 times v. The speed of the object is then the absolute value of v in the v direction. In general, we can write the vector equation in a slightly modified form. So notice that we can write it as r sub 0 plus t, which represents time. R sub 0 is the initial position, times the speed, which is the absolute value of the velocity, times the direction, which is given by the unit vector. So we continue with example 9.30, and it says, a model airplane is to fly directly from a platform to a reference point, 211, towards a point 556 at a speed of 60 meters per minute. What is the position of the aeroplane after 10 minutes to the nearest meter? So remember that in these cases, the position is given by this formula, right? R sub 0 plus time times speed times the unit vector. So, or direction. So here we need to know what these different variables are, and then we just plug them in, right? So r sub 0 is going to equal 211 because that's the initial reference point. And then we know that the velocity vector would be given by the position at the second point minus the position in the first point. So that's going to be 3, 4, 5. That's simply subtracting 5 minus 2, 5 minus 1, and 6 minus 1. Then we can find the absolute value of this, or the modulus, and this is going to be the square root of 9 plus 16 plus 25, which is the square root of 50, and this is equal to 5 square root of 2. Then the unit vector is going to be the vector v divided by the magnitude of v. So this would give us 3 over 5 square root of 2i plus 4 over 5 square root of 2j plus 5 over 5 square root of 2k. And then we're ready because all we have to do is plug the information in. So we would have that the position at time t is going to equal r sub 0, which is 2i plus j plus k, plus, and time, and this is minutes, so 10 times the speed, which is 60 meters per minute, and this times the unit vector, which we just found, right? So that's going to be, again, 3 over 5 square root of 2i plus 4 over 5 square root of 2j plus 5 over 5 square root of 2k. And then if we do all this multiplication and then we add the similar terms, and then we round to the nearest meter, we're going to get that the final position is approximately 257 for x, 340 for y, and 425 for z. So next we have example 9.31, and it says an object is moving in a plane of an appropriately fitted coordinate system such that its position is given by r is equal to 3, 1, that's the initial position vector, plus t times minus 2, 3, where t is the time in hours after start and distances are measured in kilometers. Part A, find the initial position of the object. So the initial position of the object is obviously going to be the coordinate 3, 1, which we can see here. Show the position of the object on a graph at the start, after 1 hour, and after 3 hours. So notice that here we have the position of the object at the start. That is when t is equal to 0, as we can see here, and it gives us the position 3, 1. When t is equal to 1, we will get that the position is 1, 4, which is represented on the graph right here. And then when time is equal to 3 hours, we substitute t for 3, and we find the coordinates minus 3, 10, which is represented by this point on the graph. Now for part C, they want us to find the velocity and speed of the object. So we know that the velocity is the vector in here, right? So velocity is simply going to be equal to the vector minus 2, 3, which can be interpreted as every hour, 2 units west and 3 units north. The speed is equal to the magnitude of v, which we know is going to be the square root of 4 plus 9, and this is equal to the square root of 13. So square root of 13 kilometers per hour. Now notice that we could also express the velocity as being equal to the square root of 13 kilometers per hour in the direction, because remember that speed, the difference between speed and velocity, as those of you who are in physics know, is that it's speed with direction. So we have to mention the direction. We would say that square root of 13 kilometers per hour in the direction of minus 2, 3. So the next topic in this section is distance from a point to a line. Now, I don't know if you guys recall, but last year we did a proof that resulted in this expression. This is in a Cartesian plane, which is 2 dimensions. So if we have a line written in the form ax plus by plus c equals 0, then the distance between a point P and the line L, which we can see on the graph here, is equal to the absolute value of a times x sub 0 plus b times y sub 0 plus c over the square root of a squared plus b squared. In the 3-dimensional space, you're going to find that the distance is equal to the absolute value of a vector L, which lies on the line L, times, this is cross product, the vector AP. Now AP sub 0, which is the point that you see here. So this vector is given from point A to point P, the absolute value of that over the magnitude of vector L. Now, why is that? Notice that we can say that this distance d, using trigonometry, is equal to the magnitude of this vector, which is a p sub 0, times the sine of the opposite angle theta, but we know that the sine of theta is equal to this expression, and that's why we end up with this. So we continue with example 9.33, and it says, find the distance from the point 1, 3 to the line with equation 2x minus y is equal to 7. Now this is obviously in 2 dimensions, right, or the Cartesian plane. Therefore, the formula we need to use is distance is equal to the absolute value of a times x sub 0 plus b times y sub 0 plus c, and this divided by the square root of a squared plus b squared. So it's just a matter of substituting the information into this equation. Now here, if we rearrange this, notice that we get 2x minus y minus 7 is equal to 0. So it's easy to identify a, b, and c, right? A is 2, b is negative 1, and c is negative 7. Now obviously this would be x sub 0 and this is y sub 0. So the distance is going to be equal to the absolute value of 2 times 1, so 2 times 1 plus b is negative 1, so negative 1 times 3 plus minus 7, and this over the square root of a squared, which is 4, plus b squared, which is 1. So in the end, we're going to get that the distance is 8 over square root of 5. We continue with example 9.34, and it says, find the distance from point P, 8, 1, negative 3, to the line containing M, 306, and N, 5, negative 2, 7. So this is in the 3-dimensional plane. So let's recall the theorem, right? So we have a line L and a couple of points on that line, in this case M and N. And then a point P, and we want to find the distance from point P to the line. Now, this has to be a right angle, right? And then we would also have this, and we said that through trigonometry, we know that the distance is going to equal the absolute value of the vector mn, in this case, this vector here, mn, times cross product vector mp, which is this vector over here that represents the distance between m and p, and this divided by the magnitude of vector mn. So we would need this magnitude here. Now, first of all, let's find vector mn. So vector mn is obviously going to be points m, or the point m minus the point n. And from that, we're going to get that this is 2, negative 2, and 1. And then we're going to find also that vector mp will give us 5, 1, and negative 9. So that means that we have all the information we need, because the distance is going to equal the absolute value of the cross product of mn, so 2, negative 2, 1, cross product mp, which is 5, 1, and negative 9. And this divided by the magnitude of mn. So that's going to be the square root of 2 squared, which is 4, plus negative 2 squared, which is 4, plus 1 squared, which is 1. So notice that if we do the cross product and then find the magnitude of that, it's going to be the square root of 17 squared plus 23 squared plus 12 squared. And this over the square root of 9. And in the end, we're going to get that the distance is equal to the square root of 962 divided by 3. So that's the distance d between the point P and the line containing points M and N. So now let's take a look at distance between two skew straight lines. In figure 9.38, two skew straight lines L1 and L2 are shown with direction vectors V1 and V2 respectively. So we can see the lines L1 and L2 and the direction vectors V1 and V2. We need to find the distance d defined as the length of the common perpendicular between them. Consider any two fixed points, P1 on L1 and P2 on L2. The distance d is the length of the orthogonal projection of vector u, which is equal to the vector P1, P2, on a direction perpendicular to both V1 and V2. This direction can be determined by the cross product of V1 times V2. So notice that the distance, this distance d, is equal to the absolute value of the magnitude of the vector P1, P2 times the cosine of theta. We can see that here. Cosine of theta times the magnitude of u, which is the same as the vector P1, P2, would give us d. Now, we know that the cosine of theta from the previous section is equal to this, so we end up with this expression. That means that the distance is equal to the absolute value of the vector P1, P2 times the cross product of vector 1 and vector 2 divided by the absolute value or the magnitude of the cross product between vector 1 and vector 2. So now we do example 9.35, which will be the last one on this video. And it says, find the distance between the following skew lines. And they give us a line 1 and a line 2 in vectorial form. Recall that the distance between two skew lines is going to equal the absolute value of the vector between points 1 and point 2 times, or dot product, of vector 1 cross product vector 2, and this divided by the magnitude of the cross product of vector 1 and vector 2. So first of all, let's notice that point 1 here would be 2, 3, 1, and that point 2 would be 4, 2, and 0. We can see that here and here. So that means that the vector P1, P2 is going to be the difference between these 2 points, which would give us 2, -1, -1. Then we also have that vector 1, the direction vector 1, is going to be 1, 2, -3, and the direction vector 2 is going to be 3, -1, and 1. So notice that if we do the cross product of vector 1 and vector 2, this is going to give us -1, -10, and -7. Therefore, the distance is going to be the absolute value of the dot product between the vector 2, -1, -1, and the cross product of the vectors v1 and v2, which we found was -1, -10, and -7. And this divided by the magnitude of that cross product. So the magnitude of -1, -10, and -7. Now notice that this is going to give us the absolute value of -2 plus 10 plus 7 divided by the square root of 1 plus 100 plus 49, And then if we do the math here, this is going to give us the square root of 6 over 2.